Okay, so yesterday we were looking at the idea of resource sharing, and in particular the approach that we are taking in order to implement resource sharing is a technique that is sometimes referred to as folding. The idea being that you have a set of operations that need to be completed and you have a finite set of hardware resources. You are going to fold multiple operations onto the same hardware resource so that the hardware resource can be time multiplexed, and over a certain number of clock cycles will finish all the iterations required and all the operations required to complete one iteration. Okay. So what we are going to do today is to look at a couple of more examples of folding, or rather go a little bit deeper into how the folding can be implemented in practice. Okay. So to start with, what I am going to do is once again just review the example that we took up yesterday, which is just adding three streams together. So A, B and C are three streams of data, meaning that they are sampled sequences of data. I want to add all of them together, first A and B, and then add that result to C and generate y of n. Okay. Now to implement folding, we are going to focus only on what are the actual functional operations that need to be implemented. So in other words, when I draw the data flow graph corresponding to this, I am not going to worry about the sources. I am not going to draw a node to indicate that there is a source over here and that some data is coming from this source, because from a functional point of view there is no hardware unit associated with that. So if I draw the equivalent data flow graph, essentially it will just look like this. There is one addition and there is another addition. Okay. I am not even going to draw the incoming edges because those are essentially just coming from sources, from external sources. There are no other dependencies as such. So for all practical purposes, I can just assume that the addition A1 can execute at any point in time because the A of n and B of n values are already going to be present. The only restriction that I really have as far as this data flow graph is concerned is A2 can execute only after A1 for a given iteration. So that is pretty much all the information that is being captured by this data flow graph. Okay. Now let us take this data flow graph. The hardware that I have available is an adder pipelined to depth 1, which essentially is something that looks like this. There is an adder and a register at the output. It takes two inputs and it generates one output. This is what I am assuming is the hardware unit available to me, only one type of hardware. Okay. And since I have already assumed that there is a register at the output, I am not really going to bother with talking about a critical path as such. I am just going to say basically that this adder has a latency of 1 clock cycle and an initiation interval of 1 clock cycle. Okay. And what is the duration of that clock cycle, how many nanoseconds or how many picoseconds, I do not really care. I am not mentioning that at the moment, because my assumption is that I am going to use this in a clocked system where that clock will be sufficiently long period so that there is no violation of timing over here. Okay. So with this assumption, what I am going to do is, now if I want to create an equivalent hardware representation for this, I need to first choose my folding factor n. So let us start with a folding factor of n equal to 2. What that effectively means is that the time instants or the scheduling instants, right, the times at which the two operations A1 and A2 are scheduled must fall within the values 0 and 1. Okay. In other words, n equal to 2 essentially means that I am alternating 0, 1, 0, 1, 0, 1, right. Those are the two phases of operation. Okay. So any of the operations A1 and A2 need to get scheduled in either time 0 or in time 1. Okay. And also, as we discussed yesterday, from just observing this data flow graph, we can pretty much see that A2 has to happen after A1, right, and in fact one cycle after A1. From that, what we can see is the only possible choices, only valid choices are that T of A1 is equal to 0 and T of A2 is equal to 1, where T of a node is the time instant at which it is scheduled. Okay. These are the only choices which allow us to satisfy the constraints under this particular implementation. So now let's go further with that, and how do we translate this into a complete hardware architecture. Okay. Once I have these two numbers, what I can say is, let's look at the link from A1 to A2. A1 is now scheduled at time 0, A2 is scheduled at time 1. A1 is scheduled at time 0, meaning that the output of A1 will be ready at time 1, because my hardware is such that after I give the inputs, it adds and then puts it into a register, and the output actually is available only on the next clock cycle. So for this edge A1 to A2, what I essentially end up having is A1 scheduled at 0, output is ready at 1, okay, and A2 is scheduled at 1. Okay. So what I am going to do is define a term over here saying that df, right. The idea of df is simply, are there any extra delays or registers required on the edge connecting A1 to A2, okay. And in this case, the df from A1 to A2 I define as the time when A2 is scheduled minus the time when A1 finishes, right, where this PA is the pipeline latency of an adder, which is equal to 1 time unit, right. And in addition, I am going to say that if there were edges, or rather if there were actual delay tokens present on the edge between A1 to A2, then it gives me extra time. In other words, A2 is now dependent on 1 iteration earlier or 2 iterations earlier, or in general W iterations earlier output produced by A1, right. If A1 produces its first output at T of A1 plus PA, it would have produced the previous output at T of A1 plus PA minus N, right. So let's take a moment to understand exactly what this equation is saying. I have defined one term df, okay, and over here what I am saying is the value of that df is the time when A2 is scheduled minus the time when A1 finishes, okay. So if that number is not equal to 0, what it means is after A1 has finished, I need to take the data output from A1 and save it somewhere. I need to store it in some registers until A2 is ready to use it, okay. If that number is negative, there is a serious problem. That is not acceptable, okay. It basically means that I am violating a constraint. The additional thing that I have over here is just this second part, which basically says, if there were token delays present on the A1 A2 edge, meaning that A2 depends on 1 iteration previous sample of A1, then I actually get some extra freedom. I can add W times N or 1 times N to this df value. Effectively what it is saying is, look, I computed the value of A1 in one previous iteration, I then just store it for N extra cycles and you then use it for A2. The interesting thing is, what this allows you to do is T of A2 can now be less than T of A1, right. If this W is greater than 0, in other words, I do not care if this T of A2 minus T of A1 plus PA is negative, because the W might be sufficient to bring it positive. Let us walk through this example, complete it. In this particular case, what I have is that df from A1 to A2 is T of A2 is 1, T of A1 is 0 plus PA is equal to 1, and the W in this case is 0 times N, which means that df is equal to 0. Translate that into equivalent hardware. My hardware now looks like this. I have an adder. This is my pipelined adder unit. All that I am saying over here effectively is, the two inputs over here, rather than drawing multiplexers, I am going to use a slightly different notation. I will use some kind of switches to basically indicate that these are switches that are sort of rotating across different phases, 0, 1, 0, 1, 0, 1 and so on, right. A multiplexer is how it is finally going to get implemented, but visually sometimes it is all another way of looking at it is to think of it as rotating switches where you are just going through different phases cyclically. Okay. So, for that what we say is there is a phase 0 and a phase 1. Similarly, there is a phase 0 and a phase 1. Now, according to this schedule that I have got over here, A1 addition occurs at time 0, which basically means that how do I get that to happen? I make sure that A of n and B of n are given as the two inputs to the adder at time 0. A of 2 occurs at time 1, which means that I need to make sure that C of n and the output of the adder with 0 extra delay elements associated with it needs to be fed back over here at time 1. Okay. So, this is where that df comes into the picture. In this case df is equal to 0, so there are no extra registers required on this edge.